Akihiro Munemasa from Tohoku University, who is actually our regular participants of almost all conferences which was held in Novosibirsk, online or in person. And this talk will be about extending double covers of non-symmetric association schemes of class 2. So the floor is yours.
Yeah, thank you. I think everyone can hear me. Okay, so thank you very much, Elena, for invitation to give a talk here. So if I understand correctly, so today session is devoted to the theory of association scheme. So as a first speaker, let me present a small result, maybe just a small observation on the rather easy kind of association scheme. So, so let me explain the non-symmetric association scheme of class 2. It's rather long name, but it's quite well-known object. And today I want to show you the extended double cover of such association scheme. And it turns out to be a non-symmetric association scheme of class 3, which is antipodal. Okay. So non-symmetric association scheme of class 2 is also known as many other different combinatorial objects. Notably, this is essentially equivalent to skew-Hadamard matrix. So if you are already familiar with the theory of association scheme, then it's you may think of just of association scheme as a collection of adjacency matrices. One is identity, and two adjacency matrices A1, A2. These two 0-1 matrices are transposed to each other, satisfying certain regularity conditions. And with this regularity condition, if you construct this matrix H here, so I just have to add one extra column and one extra row, then this becomes skew-Hadamard matrix. That means it's a Hadamard matrix in the usual sense, and it's almost skew-symmetric, except the diagonal are all 1. And conversely, if you have a skew-Hadamard matrix, and if you normalize first column and first row in this manner, all 1 and -1 here, then you can recover a non-symmetric association scheme class 2 in terms of this lower right corner. Now, the digraph represented by the adjacency matrix A1 is also called doubly regular tournament. A tournament just means that it's essentially a complete graph if you ignore the orientation, but every edge has unique orientation. So that is a tournament, and doubly regular just means that it satisfies the regularity property imposed by being association scheme. And the construction of such doubly regular tournament is also known from Paley. It is also called a Paley digraph, and it is constructed as a Cayley digraph on the finite field with Q elements, where Q is congruent to -1 modulo 4. Incidentally, the tomorrow's session is devoted to Paley graph, but this is not the Paley graph in the usual sense, but it is a digraph. So you may think of any of your favorite concept and regard non-symmetric association scheme as just a part of main part of skew-Hadamard matrix, or doubly regular tournament, or Paley digraph, and so on. So already I present our main theorem. So let identity I1, A2 be the set of adjacency matrices of a non-symmetric association scheme class 2 on M points. So each of these matrices, A1, A2, they are M by M matrix. It is enclosed by 0 and 1s. They are just one row or one column. So the total number of rows or column is 2m plus 2. So C1 is a square matrix of order 2m plus 2, constructed from A1, A2, and 0 and 1s. And the C2 is defined to be transpose of C1. C3 is J minus I minus C1 minus C2. So that if you add identity and C1, C2, C3, you get all one matrix J. And the claim is that this set of 4 matrices is the set of adjacency matrices of a non-symmetric association scheme of class 3 on 2m plus 2 points. It's not difficult to observe that this C3 is actually a permutation matrix. So one could call this association scheme antipodal double cover, hence the name extended double cover. So we call the resulting association scheme the extended double cover of the original association scheme. I forgot to say that this, I forgot to write that this X is named for the original association scheme. So let us recall a definition of association scheme, because the talk follows today about association scheme. So for me, association scheme is a pair of a finite set X and a collection of binary relations on X, which partitions X times X, satisfying the following 3 conditions. The first is the R0 is a diagonal relation, and for every I, there exists I prime, such that if you transpose the relation Ri, then it becomes one of the other relations. And for every triple ijk, this pijk, this is also called intersection number or parameters of association scheme, and it's independent of the choice of xy. So this number counts the number of z, which satisfy the 2 conditions: xz belongs to Ri and zy belongs to Rj. Now, each Ri is a binary relation on X, so we can construct an adjacency matrix AI, which is a square matrix whose rows and columns are indexed by X. And then the third condition amounts to the matrix equation that AI and AJ, if you multiply as matrices, then it expands like the linear combination of all the adjacency matrices with coefficient being intersection numbers. And since I'm mainly concerned with the non-symmetric association scheme, so I need to define what I mean by symmetric association scheme. It just means that each relation Ri is symmetric, and otherwise scheme is called non-symmetric. So that's enough for the definition of association scheme. So the crucial condition for association scheme is that the third condition that imposes some regularity. The second condition in our case for the non-symmetric association scheme is rather obvious one, that the A1 transpose is A2. So in our main theorem, the point is that if we impose some regularity condition in the binary relation, or some condition on A1, A2, that is how we can multiply A1 and A2 for or also A1 square and A2 square, then we can actually compute the the products of these matrices Ci, so that we can verify that the resulting set I identity C1, C2, C3 is the set of adjacency matrices of a non-symmetric association scheme of class 3 on 2n plus 2 points. Now, actually, the proof of the theorem is rather easy. So let me spend the rest of my time on putting our theorem in the proper context. So first of all, because of the name I chose was extended double cover, this comes from a known construction of association scheme, which one could call doubling. So this is due to Dima-Pasechnik. So we start with a non-symmetric association scheme of class 2, and let the number of points be m. Then this time we construct some in a similar manner that a matrix, but the resulting matrix size 2m plus 1. So I add just one extra row and column, and then arrange A1, A2 in appropriate manner, but I also here add identity matrix. So that's the definition for A1 tilde, and A2 tilde is just a transpose of A1. It turns out that the identity plus A1 tilde plus A2 tilde is the O1 matrix, and this set of 3 matrices form the set of adjacency matrices of a non-symmetric association scheme of class 2. The difference is that we start with such a scheme on m points, then we obtain 2m plus 1 point scheme. So it's not exactly doubled, but nearly doubled. So this is why we know, this is why we call it doubling. And remember that the non-symmetric association scheme is essentially the same as skew-Hadamard matrix. So this construction allows construction of skew-Hadamard matrix of twice the order given as skew-Hadamard matrix. So this is why it is called doubling. But our construction is slightly different because we have a class 3 and 2m plus 2 points. Well, of course, both the number of classes and the number of points increase by 1, but there is no such natural construction of increasing the number of classes and number of points by 1 in the theory of association scheme. So that's why our theorem is not a trivial consequence of doubling. It's rather different construction. So this was our theorem shown once again. And now let us focus on a different part of the theorem. Here, non-symmetric. I assume that the scheme be non-symmetric, and the resulting scheme is also non-symmetric. Now, what happens if we assume it is symmetric? Well, symmetric association scheme of class 2 is nothing but a strongly regular graph. And then, given a strongly regular graph, can we construct a symmetric association scheme of class 3 on 2m plus 2 points by similar construction? Well, it turns out that this symmetric counterpart, the symmetric analog of this theorem, is classically known. It's a rather old result due to Donald Taylor in 19 77. Well, although it's somehow formulated differently. So instead of starting with a non-symmetric association scheme, we start with a symmetric association scheme on class 2 on M points. So if you are familiar with the theory of strong irregular graph, this is nothing but a strong irregular graph with parameter k, lambda, mu. These are the coefficients appearing in the expansion of A1 squared in terms of identity A1 and A2. There is an additional assumption, k has to be equal to 2 times mu. Not every strong irregular graph satisfies this condition, but some satisfy. So under this condition, we define matrices D1, D2. It's quite similar fashion, but we want the symmetric matrix, so it's slightly different from the non-symmetric counterpart. Here, the position of all one vector deliberately different in terms of row and column to make C1 non-symmetric, but the D1, it's symmetric. So D2 is not the transpose D1, so D2 had to be defined separately, and D3 is automatically determined to be J minus I minus D1 minus D2, and it turns out that D3 is a permutation matrix. So the collection of these 4 matrices is the set of adjacency matrices of a symmetric association scheme of class 3 on 2m plus 2 points. So the graph with adjacency matrix D1 is called Taylor graph, and it is an antipodal distance regular graph of diameter 3. In fact, it's an antipodal double cover. So because this theorem classically known, our result on non-symmetric analog is our result is a non-symmetric analog of this Taylor's construction. Now, I have, one more slide. So what we have done is that we start with a non-symmetric association scheme of class 2 and call it X. Dima Pasechnik invented a construction called doubling, which almost doubled the number of vertices, number of points, but still the resulting association scheme has class 2. What we invented was the extended double cover, which is a association scheme of class 3. So somehow similar, but a different construction. One could first apply this doubling and then extended double cover of doubling. And then certainly you obtain association scheme of class 3. But then there may be a straight way to double the extended double cover. So forget about the original non-symmetric association scheme of class 2, but we could start with the extended double cover, that is an association scheme of class 3, and directly construct what you would get by doubling and extended double cover. Well, after some calculation, this can be described easily, that the extended double cover of a doubling can be described in terms of the adjacency matrix. Adjacency matrix is C1, C2, C3 of extended double cover. So if we arrange the C1, C2, C3 inside this block matrix C1 prime in this manner, and define C2 prime to be the transpose C1 prime, and you have no choice, and C3 prime is a diagonal join of C3, then this turns out to be the extended double cover of a doubling. So this is just how we, the direct description of the composition of two construction. Yeah, but this seems to suggest that there may be a symmetric analog of this construction, but it seems there's none. So if we start with a symmetric association scheme instead of non-symmetric, with a proper assumption that k equal to mu, so that we can construct a Taylor graph, then this extended double cover is a Taylor graph. We don't have a doubling of a strongly regular graph, but since we have described this down arrow purely in terms of extended double cover, so it might, you might hope that the given a Taylor graph, it may be possible to construct a Taylor graph with twice the number of vertices by mimicking this construction. But so far we were unable to find it. There's such a construction, and I don't think there is such a construction, because that would mean that given a Taylor graph, you always get a Taylor graph with twice the number of vertices, and that doesn't seem to be the case. Okay, it's a bit early, but that's all I want to say. So thank you very much for your attention.
Thank you very much for your talk. Are there any questions to the speaker?
Yeah, Paul,
Akihiro,
yeah.
I think it's easy to compute the intersection numbers of the extended double cover.
Sure, yeah.
Do you happen to have the table on your hand to show us, or is it?
Okay, it's more compact to describe the eigenmetrics, but I'm not sure. But okay. I can show you. Yeah, but by the way, our paper is now available on archive.
Okay, good.
So let me just.
I can check that out.
Yeah. Sorry, I should.
Strong relationship to the intersection numbers of the original.
Yeah, sure.
Yeah.
I will find out. I forgot to say that the for non-symmetric association scheme, the intersection numbers are uniquely determined by the number of points. So the formula for the intersection numbers are quite easy. It depends on one parameter, which is the number of points.
Okay.
Yeah, but the symmetric case, the strongly regular graph parameter of the strongly regular graph are not determined by the number of points. So there are more, the intersection number is involved. Well, of course, it's not that easy, but it's not that difficult. But
right, thank you.
Okay, any other questions? Well, if not, then let us thank Akihiro again for these new ideas.
Thank you.
Sharing with us this interesting construction. Actually, do you think are there any other examples of graph for which this construction can be applied?
I didn't find any. I don't know.
I see. Okay, thank you very much. Thank you for this interesting talk. Thank you.